So let's start with the modeling of this bridge. These are the plan and elevation of the bridge drawings, and these are the beam section properties, and this is how the cross section of the bridge looks like. It has 5 girders and the center to center spacing of each girder is 9 feet. So let us model this kind of bridge in MIdas Civil. First of all, we'll create a new project in MIdas Civil by going into File, New Project. Then we'll set the unit system. So I'll go to Tools, Unit System, and I'll set the unit system as inch kips. The first step is to define the material properties in MIdas Civil. So for that, we'll go to Model, Properties, Material, and we will select the type of design as concrete, and we will select the standard as ASTM reinforced concrete standard, and we are going to select the grade as C5000 for the girder, and we are going to select the grade C4000 for the slab. So I'm selecting the standard C4000. Now we will define a steel material for the tendon. So I selected a steel material for the tendon. The second step is to define the section properties. Since it's a composite type of bridge, we are going to define the composite type of section in MIdas Civil. For that, I'll go to Model, Properties, Section, and I'll click on Add, and I will go to the Composite tab. I will give it a name, Section AA. So basically we have two different type of sections in the drawings. This is section AA and section BB, so we are going to define these two sections, and then we'll ask MIdas Civil to automatically create the tapered section between AA and BB. So I will first define section AA. The type of section is composite I. I will punch in the properties of the slab width of the bridge, which is 536 inches. The girder number is 5, the CTC is 108 inches. Again, the slab width is 108 inches. The thickness of the slab is, I am assuming, to be 10 inches. Haunch thickness is, I am assuming it to be 1 inches. I will check on the symmetry because the girder is symmetric about this axis, and I'll be checking on two joints that I need to define the section. Now I'm going to define the section properties. So I will punch in the properties for HL1 and HL2 and so on and so forth. You can obtain what is the value of HL1, HL2, etc. from the drawing on this site, and you can compare it with the beam section drawings that you have, and you can obtain the section properties. So now I am punching in the parameters. HL4 would be 6.5 inches, HL4-1 would be 3 inches, HL5 would be 9 inches, BL1, half the thickness of the web, would be 4 inches, BL2 would be 24 inches, BL2-2 would be 20 inches, BL4 16.5 inches, and BL4-1 would be 12 inches. I will select the different materials for the slab and the girder. Slab would be grade C4000, girder would be grade C5000, and I will change the offset to center top, and I can see the calculation results of the girder before and after it becomes composite. And once I click on OK, the section will be defined. Similarly, I will define the section BB. So I'll copy section A and modify the HL5 to be 43 inches, and this is the only modification that we need here. So I'll check on the symmetry, and HL5 here would be 43, and I'll click on OK, and the section has been modified. I'll just modify the name again. Okay, so this is how I have defined two different sections. To define the tapered section between A and BB, I'll again add a new section. I'll go to Tapered tab, and I'll go to the composite I type of section here, and I'll give it a name, 2 here section. So the section would be from section AA to BB, so I'm writing a name as section AB, and I will punch in the number of girders as 5, CTC as 108 inches, the slab thickness as 108 inches, the thickness of the slab as 10 inches, the haunch depth as 1 inches. I will first import the size I as section AA, and I'll import the size J as section BB, and I will select the material for the slab and the girder. So this is how I'm selecting the material for the slab and the girder, and I will change the offset to center top again, and I can see the section properties for I and J end respectively. And once I click on OK, I have defined the two pair section AB. Now I'm going to import all of the sections from the model file that we generated earlier. So this is how you can create other sections in MIdas Civil. So I'm just going to import, and I'm gonna import all the sections. So this is how I have imported other sections. We have section tapered from A to B, B to A for the first pair, and same thing for the second pair. So when I go to the works tree now, you can see that we have 3 different materials and 6 different sections. Now we will define one girder, and we are going to copy one girder in the transverse direction to obtain other girders to model the full width of the bridge. So first step is to go to model structure wizard beam, and I will model the full length of the bridge. It's gonna be modeled in 94 different elements having the length of each element as 5 feet. I'm going to assign a material properties of grade C5000 and the section property as section A to whole of the girder. So this is how it will be modeled. Once I click on OK, you can see that the girder has been modeled, and you can see that on the top of the girder we have a plate which represents the slab. Now I'll go to the side view, and I will see that as of now we do not have any tapering in the girder. So I'll define the tapering in the girder by assigning different sections at different locations. So first of all, let's define the support to this bridge so that we can easily see where the tapered profile of the girder has to be assigned. For that, I'll go to model, properties, section. Oh, I'm sorry, it has to be model, boundaries, supports, and I will assign a support, let's say restraining dx dy dz on node 1. Now I'll define another support at node number 30. So I'm checking on the node number, and I'm gonna select node number 30, and I'll define dy dz restrain. Then I'll go to node number 95, which is the last node. I'm gonna define dy dz again, and for the second pair it has to be 145 meter away from node number 94. So let's see which node has this distance. For that we would use the query command in MIdas Civil. I will query between different nodes, and it will give me the distance between node number 95 and the required node. So I clicked on node number 95 and node number 65, and you can see that the distance comes out to be in inches. If you want to see the distance in feet, just change the tool system to feet. Just type in node number 95 and 65, and you can see that the distance is 150 feet. So 66 is the node on which we have to apply the support. This was to demonstrate to you that how you can obtain the distance from MIdas Civil. So I will select node number 66, and I will assign the support accordingly. So this is how I have defined the supports in MIdas Civil. If I want to see all the supports that I have defined, I can go to display, and I can go to boundary, and I can activate the support. Once I click on OK, I can see all the supports on the girder that I have. Now I'll define the tapered profile of the bridge. For that, I will select the elements on which I want to define the tapered profile. So these are the elements where I want to define the tapered profile on pair 1, elements number 21 to 29, and I will assign them 2p section AB, and similarly I will assign the tapered section on the right side of the second pair, and I will assign the section properties as 2p section BA. Similarly, I'll do the same thing for the second pair. I will select the elements on which I want to assign the tapered section, and on the right. So this is how I have defined the tapered section in MIdas Civil. It's pretty simple. Just select the elements and drag and drop the new section properties. But as of now, you will see that it is not a perfect tapering. The section AA must be at this cross section, and section BB must come at the top of the support. So for that, I will go to Model, Properties, Tapered Section Group. I will select all the elements which are in the tapered section group, and I'll tell the program that they belong to the same group. And now you can see that the perfect tapered profile has been assigned to the girders. Similarly, we'll do the same thing for the second pair, and you can see that the section have become perfect tapered in MIdas Civil. So this is how you can define the sections to be tapered easily in MIdas Civil. Now we will copy all these girders that we have defined in the transverse direction of the bridge to model the whole width of the bridge. For that, I will go to Model, Elements, Translate. I will select all elements by going to this option, Select All, and I will translate them in the Y direction by a distance of 9 feet, and I'll copy them by 4. Number of times would be 4, and I will ask the program to copy the node and the element attributes. So once I click on OK, you will see that you have created the whole width of the bridge, and you will see that on the top of the girders we have the slab too. But if you see the line beam model, you will see that there is no connection whatsoever between the girders in the transverse direction, because the composite section will model the slab for you in the longitudinal direction of the bridge, but for the transverse direction you have to consider the slab stiffness by using the beam elements, because it's a grillage model. So now we'll create the beams in the transverse direction. So for that, first of all, I'll define a section property. I'll go to Model Properties section, and I will click on Add, and I will define a rectangular type of section. I will give it a name, Transverse, and I will put it as user type. The H would be 10 inches, so I'm approximating it as 0.8 feet, and the width would be 5 feet because the distance between the two adjacent nodes is 5 feet. Once I click on OK, you can see that the transverse section has been defined, and now we'll create the elements. For that, I'll go to Model, Elements, Create Elements, and I will select the material as the material of the slab and the section as the transverse section, and I will create the elements like this. Now I'll copy these elements in the longitudinal direction. I'll go to Model, Elements, Translates. I will select the recently created elements by selecting recent entities, and I will translate them by 5 feet. The number of times would be 94, and I will click on Apply, and you will see that the grillage model is complete. So this is how you have completed the grillage model for this bridge. Okay. One thing that I want to point out is that you can see that the perfect tapering doesn't appear in the other girders. For that, you need to select individual girder and define the tapered section group for the elements on which you want to make the tapered section. So you can do it very simply. Just go to the top view, select any girder for which you want to define the tapered section group, and go to View, Activities, active, so it will become active and it would be easier for you to work with this girder. You can go to model properties, tapered section group, type a name, let's say tapered 5, select the elements which are in the tapered section 5, click on add. Similarly, do the same exercise for other elements. Tapered 6, click on add. Tapered 7, click on add. Tapered 8, click on add. So this is how you can create the perfect tapering for other girders. If I activate all the girders now, you can see that on the second girder again we have the perfect tapering, and we have to do the same thing for the other remaining girders. Now let us see how we can define loads in MIdas Civil. Since it's a spliced girder type of construction, we have to model the construction stages in MIdas Civil. For that, groups are very important. So first of all, I'll define different groups that I need in my model. So I will define the construction stage groups from 1 to 6. I will click on add, and you can see that the 6 groups have been defined. In the boundary group, I will define 2 different boundaries, support, and if I want to define a temporary boundary, I will name it as temp. I will define different load groups, first for self weight and the other one for barrier load, and I'm gonna define different pre-stressing in different stages. So I'm gonna define pre-stressing 1 to 6 groups, and this is how the groups can be defined easily in MIdas Civil. So just right click, go to new, it will define one group, go to new dot dot, you can define multiple groups at the same time. For defining the load case, first go to load static load cases and give a name to the load case. So first we are going to define the self weight load case, and I will select the type as dead load. Again, I'm gonna define the name as barrier load, and it's gonna have the type as dead load again. Then I'm gonna define the load case for pre-stressing, and the load type would be pre-stressing. So you can select the load type as pre-stressing, click on add, and you can see that 3 load cases have been defined in the model so far. Now I'll go to load self weight. This command will automatically determine the self weight of the element and it will assign it to the model. So I will select the load case name as self weight, the load group name as self weight, and I will assign a factor of -1 in the direction of gravity, and this is how the self weight has been assigned in the model. And when you go to the worktree under the self weight load case, you can see that the self weight has been defined. Now let's define the barrier load. For that, I'm gonna go to load element beam loads. So I will select the element beam loads. I will select the load case as barrier load, the load group name as barrier load again, and I'm gonna define an eccentric loading to the barrier. So I'll check on eccentricity. Eccentricity will be in the global y direction, and I will define the eccentricity as, let's say, 4 feet from any girder. So I will select the girder where I want to define the eccentric loading for the barrier. I will select the girder and I will punch in the value for the barrier that we have, and once I click on apply, you can see that eccentric loading has been applied to the model. So this is how you can define the eccentric loading very easily in MIdas Civil. If you do not want eccentric loading, you can check off the eccentricity as per your will. So this is how we have the model so far. Right now we just have the basic structure, the basic grillage model for the bridge. We have defined different supports and we have defined the different load cases that we need in our model. Now we need to define the pre-stressing. For defining the pre-stressing, I will first go to load and pre-stress loads, and I'll go to tendon property. So I will define a tendon property. I will give it a name, tendon, and in this bridge we are going to define 2 different types of tendon properties. First is a pre-tension type of tendon, and the second one would be a post-tension type of tendon. So I'm defining a pre-tension type of tendon. The number of strands would be 12, and once I click on OK, you will see that the pre-tension tendon has been defined. I will give it a name pre-tension so that I can distinguish between the different tendon properties. Now I'll define a post-tension type of tendon, so I'll give it a name tendon post-tension, and I will define the material, the number of strands that we have, and the duct diameter. And once I click on OK, you can see that we have two different tendon profiles in this model. Now we will assign the tendons to different elements that we have here. So first of all, let me activate girder number 1 only, and I will assign the different tendons that we need in this girder. So I'm deactivating all other parts of the model, and I'm just keeping the first girder so that I can define the tendons easily in it. Now I am assuming that this bridge has been constructed in 5 different stages. The first part is this segment, which would be installed. In the second construction stage, this segment would be installed. In the third construction stage, the left segment would be installed. In the fourth construction stage, the right segment will be installed, and in the fifth construction stage, the middle segment will be installed. And these different segments will already have some pre-tension type of tendons, so we will define some pre-tension type of tendons in these segments, and on the other segments too we are going to define pre-tension tendon. And once all the girders are installed, we will have a post-tension type of tendon running all through the length of the bridge. So I will unselect all of them. First of all, we'll define the pre-stressing one for segment 1. So for that, I'll go to load, pre-stress loads, tendon profile. I'll click on add. I'll give it a name, let's say 1 segment tendon 1, and the tendon property will be pre-tension type of tendon. The assigned elements would be the segment 1 element, so I'm gonna select all the elements which are inside segment 1. Let me zoom in at this location and you can see it better. So this is how the elements have been selected, and the input type would be 3D, and I can also define the lead length of the tendon. So here I'm going to define the coordinates of the tendon. I will punch in the coordinates, and so at the mid support, the tendon is going to be at the top of the section, and once we move away from the mid support, the tendon is going to go towards the bottom of the section, because the negative bending moments would be higher at the mid supports and lower as we go away from the support, the positive moment would be higher. So we are going to define the tendons towards the bottom once we go away from the mid support. So at x equal to 0 for these segments, we are going to define the z as -4 feet. At x equal to, let me see what distance it is. So at x equal to 50 feet, the tendon will come up, and again at x equal to 100 feet, it's gonna go down at -4 feet. So x equal to 100 would be the distance from this node to this node, and I can put the profile insertion point as element number 20. So it would be like this, and once I click on OK, you can see that the tendon profile has been modeled, and you can see the tendon running from this element to this element, and it goes up at the mid support and it goes down as you move away from the mid support. Similarly, we are going to define a tendon for the second segment, so I'll name it 2 segment tendon number 1. The tendon profile again as pre-tension type of tendon, and I'm going to zoom in at the location of the second pier that we have here. So I'm scrolling to zoom in, and on the assigned elements, I'm gonna assign all the elements associated to this tendon, and I'm gonna input as 3D type. At x equal to 0 again, z would be -4 feet. At x equal to the distance of this node to this node, which would be 50 feet. It's gonna go up, and at x equal to 100 it's gonna go down again, and the insertion element would be 56. And once I click on OK, you will see that the tendon has been defined on the second segment. Now let's define the tendon on the third segment. I'll zoom in at the location of third segment again. I will give it a name, 3 segment tendon 1. The tendon property would be pre-tension type of tendon again. The assigned elements would be 1 to 19. Since this is the zone of positive bending moment, I'm gonna define the tendons at the bottom only, but depending on your tendon profile you can change it to whatever location you want. And at x equal to 95 it's gonna be at -4 again, and the insertion element will be element number 1. Once I click on OK, you can see that the tendon profile has been defined. Similarly, we'll define the tendon profile for the fourth segment. So I'll zoom in at the location of the fourth segment. I will click on add. I'll give it a name, 4 segment tendon number 1. Select the elements and punch in the coordinates. Let me see what is the distance of this node from the end node, which would be 95. So x equal to 95 and z would be -4 again, and the insertion element will be element number 76. So I'm gonna punch it as element number 76. Once I click on OK, you can see that the tendon has been defined. So in this girder, so far we have defined 5 different tendons based on the construction stages, and now we are going to define one tendon which will run all across the length of the bridge. For that, again, I'm going to go to load, pre-stress loads, tendon profile. I'll click on add. I will name it full tendon 1, and it's going to be a post tension type of tendon having all the elements in it. I'm gonna punch in it as input type as 3D, and at x equal to 0 it's gonna be at the bottom. At x equal to 145, the first pier, the first mid support, it's gonna go up. At x equal to 145 plus 90, it's gonna be 235. It would come down again because of the positive moment reason. At the second pier, at the top of the second pier, it's gonna be on the top again, and once you move towards the end of the bridge, which is going to be at 470 feet, it's gonna be at the bottom again, and the insertion element will be element number 1. And once I click on OK, you can see that the tendon running all across the full length of the bridge has been defined. Now let's see how we can copy the tendons to the location. I will activate all other elements which are otherwise inactive. So I'll active all, and let's see how we can copy these tendon to other location. So it's pretty simple. Just go to load, pre-stress loads, tendon profile, select a tendon which you want to copy, and go to copy move, select the distance. So I'm gonna define the distance as 9 feet 0, and I will click on OK, and you will see that the next tendon has been defined. So this is how you can keep on copying the tendons which have the similar profile along the transverse direction of the bridge. If you want to copy the tendons having similar profile in the longitudinal direction of the bridge, you can use the same copy feature again. The final step is to define the pre-stress load on the tendon. So I'm gonna select the load case as pre-stressing, the load group as pre-stressing 1. I'm gonna select the tendons which I need in the first stage. The load group would be pre-stressing 1. I'm going to define some random pre-stressing here, and Once I click on add, you will see that the tendon load has been defined. I'll move them back and I will select 2 segment. It's gonna be on pre-stressing 2. So I'll click on add. Similarly, I'll select the tendon on the 3rd segment, and pre-stressing 3 would be the load case. Pre-stressing 4, the segment would be segment 4, and I'll click on add. And finally, for the load group name would be pre-stressing 5, and we are going to select the tendon for segment number 5. I think I missed the tendon for segment number 5, so let us define it again. So I'll go to load, pre-stress load, tendon profile. I'll click on add. So I'll define 5, segment 1. Tendon property would be tendon pre-tensioned. The selected elements would be the ones which are at the segment 5. Okay, so first of all I need to activate the first girder, or what I can do is I can just punch in the element numbers. So let us see which elements are these. So when I zoom in at this location, it's gonna be element number 40 to element number 55. So I will punch in element number 40 to 55. 3D type of tendon input. At x equal to 0, it's gonna be at -4. And let's see what is the distance of node number, the required node number. Okay, so the distance is 80 feet, so I'm gonna punch it x equal to 80 and z equal to -4 again, and the first element would be element number 40, and this is how the tendon has been defined. Again, I'll go to load, pre-stress loads, tendon pre-stress loads. I'm gonna select pre-stressing load case, the group name as pre-stressing 5, the segment 5 tendon, and again I'm gonna punch in any arbitrary tendon pre-stress value. And finally I'm gonna select the full tendon and I'm gonna punch it, put it in the load group pre-stressing 6. And once I click on it, you have defined all the tendons that you need in your model. Okay, so this is how the tendon load group can be defined in MIdas Civil, and we have defined the tendon pre-stressing load. The final thing that we are left with is the definition of the construction stages. For that, we'll go to load, construction stage analysis data, and we'll go to define construction stage. I'll click on add and I'll active CS1, and in CS1 we are going to activate group CS1, but as of now we haven't assigned any group to the elements. So for that we are going to go to the group tab and we will select the elements that we need in individual construction stages. So I'll check on the support, I'll go to the side view, I will select the activation item as X. So all the elements which are running in the X direction will be selected. So I will select the elements for CS1, I will drag and drop to assign the elements for CS2, for CS3, for CS4, and for CS5. So this is how I have selected the elements, and now when I go to construction stage analysis data, I can define CS1, the duration will be, let's say, 30 days, and the age would be 30. So as we discussed, the age would be the age of loading of any element, so I'm putting it as 30 days. Similarly, CS2, the duration would be 30 days again. The element age, define CS3, the element age, activate CS3 element, define CS4, The duration would be 30 days. The age would be again 30 days. Activate CS4 element. CS5 duration would be 30 days. Activate element group CS5. Okay, now let's see the construction stages that we have modeled. CS1, we have the segment on the pair 1, stage 2, stage 3, stage 4, and stage 5. So this is how we have modeled the different stages of bridge. Now let us see the different boundaries that we need to activate in different construction stages. So again, I'll go to the construction stage analysis data, define construction stage. In first stage, the segment 1 is activated. I'll activate all the supports that I need, and in the load I'm going to activate the self weight and pre-stressing 1, which is pertaining to the segment 1. In stage 2, we are going to activate pre-stressing 2 for segment 2. In stage 3, we are going to activate pre-stressing 3 for segment 3. In stage 4, we are going to activate pre-stressing 4 for segment 4. And in stage 5, we are going to activate pre-stressing 5 for segment 5. So this is how I have completed the construction stage modeling in MIdas Civil for this kind of a bridge. Now let me see what construction stages that we have obtained. If you see, in construction stage 1, we have the composite section along with the slab on the top, which is undesired. So we have to tell the program that this slab has to be activated once the deck has been casted and hardened. So what we will do is, we will go to load construction stage analysis data, composite section for construction stage. I'll click on add. I will select the section, and the section 2P, section AB, will have to be activated. The girder has to be activated in CS1. So the girder material is grade C5000 and the slab material is grade C4000. For girder, the activated stage would be CS1 and the slab would be activated in CS3 after the deck on the top of it has been casted. I will define the individual stages for the girder and the slab, and once I click on OK, I have told the program, okay, these two different parts have to be activated in different construction stages. Similarly, I'll do it for 2P section BA. The same thing, I will select the active stage as CS1 for the part 1, CS3 for the part 2, the different ages for them. Now let us see the construction stage. In stage 1, now we do not have the slab on the top of the girders, which is desired. The last thing that we have to do is, we have to activate the transverse elements that represent the transverse stiffness of the deck in different construction stages. So for that, I will first create a structure group CS1 deck for segment 1, and I will select the transverse elements. For that, I'm gonna go to selection type as Y, and I will select all the transverse elements. So this is how the transverse elements are selected, and I will drag and drop CS1 deck 1 to define these elements in CS1 deck 1 element group. Now I'll go to construction stage analysis data, define construction stage. I'll go to CS3 and I will activate the CS1 deck 1 elements in this construction stage to tell the program that the deck has become composite with the girder. So when I go to CS3 now, you will see that on the segment 1, on the top of segment 1, the deck has been casted and the transverse elements appear, providing transverse stiffness to the bridge. So this is how you can model the different construction stages in MIdas Civil, and you can define different transverse elements to be activated in different stages, and you can model the casting of the deck, and you can see the results for the same. Now the last thing that we have to do is define the moving load analysis data. For that we will first define a structure group, and we will put all the deck elements inside this structure group. So I will select all the transverse elements. Since the selection type is Y, only the transverse elements will be selected, and I'll drag and drop the group deck on the top of it. The reason why we are defining this group is we have to tell the program that the load distribution takes place from the deck to the girder. So the first step is to define the moving load code, which is H2LRFT. Then we will define the moving load traffic lane. So I'm defining lane 1. Eccentricity, I'm keeping it as 0. The vehicular load distribution has to be cross beam, and I will select the cross beam group as the deck, and I will define the lane using the 2 points approach, and this is how the lane will be defined. And once I click on OK, you can see that the lane has been defined, and the lane will be defined for 2 individual wheels for each axle. Now I'll define the moving load vehicle that we want to move on this lane. We will define 2 different vehicles, HL93 truck and HL93 tendon, with dynamic allowance of 33%, and we will define a vehicle class. While defining the vehicle class, MIdas Civil will automatically determine which vehicle has higher effect on the bridge, and it will give you the results accordingly. Now we can define the moving load case. For that, I'll go to moving load analysis data, moving load case. I will give it a name, a load case moving. I will click on add. I will select the lanes on which I want to run the vehicle, and once I click on OK, you can see that the moving load has been defined. Finally, we have to tell the program that at the location of the negative bending moment areas, 2 trucks have to be considered for determination of hogging bending moment. The program can take care of it automatically. We just have to define the different groups. So CS1 pertains to the negative bending moment region, and CS2 element group pertains to the negative bending moment region. And once we do this, you can see that the different definition that we needed for the moving load data has been completed. The final thing that we are left to do with is defining the last stage, in which we are going to activate the full tendon, which spans all across the length of the bridge. So we'll go to define construction stage analysis data, and we'll name it as CX6, and we are going to activate prestressing 6 in this stage. So when you go to CS6, you will see that the full tendon has been activated. So this is how the modeling of this bridge can be done in MIdas Civil. And for detailed question, you can contact us through email, and if you need detail by detail tutorials, we can do that for you. So have a good day.